Hello, my name is Michal Polic and I'm gonna show you how to solve example test number 1. In the first task we would like to show O prime and beta prime coordinate system. We know that O prime is 0.5 times beta 1 plus 1 times beta 2. And beta 1 prime is 1 times beta 1 and minus 1 times beta 2. I'm drawing beta 1 prime as a free vector from O, but the coordinate system sigma prime will have origin O prime, therefore B1 prime will be from this origin O prime. Now we have a relationship between x in beta and x prime in beta prime. Note that x and x prime represent the same point in our figure. We can get x in beta by transforming x in beta prime by a matrix beta prime to beta plus a translation to O prime in beta coordinate system. Transformation matrix from beta prime to beta are just vectors beta prime in beta. Therefore we know the first vector and we don't know the second one. Assigning the values to our equation, we can get a beta 2 prime vector. So we can answer the subtask 2. What is the beta 2 prime vector? It is 0, 1. The third subtask is to write O in beta prime coordinate system. Therefore we can see from the figure that 0.5 times b1 prime plus 3/2 times b2 prime gives us the origin from the origin O prime. The fourth subtask is to write beta in beta prime. We know what is beta prime in beta and we can express it as an inversion of this matrix. We can find the inversion by creating an adjugate matrix and using the determinant, or for example as we do here by using linear row reduction. This way we get beta in beta prime as a matrix 1, 1, 0, 1. Now let's look on B subtask. So in here we have beta in beta prime and we should write what is beta prime in beta. We know that it is an inversion, therefore we can use the linear row reduction to find it. Therefore beta prime in beta is minus 3, 1, 1, 1/2 matrix. We can express x beta from x beta prime as well as x in beta prime from x beta. By assigning the values we can compute O in beta prime, which is the third subtask. O in beta prime is 3, 4. Let's look on the second task. We have assigned a projection matrix and we want to find K, calibration matrix, error rotation matrix, camera center and focal length. We know that the camera center is null space of our projection matrix. Therefore we can write P times C extended about 1 equals 0. By assigning the values to this equation, we see that the last column is multiplied by 1. So we want to have some multiple of first, second and third column to get a 0 vector. One possible example is to multiply the second column by 100. We see that C in delta is 0, 100, 0. Next we will find the rotation matrix R. We know that the focal length multiplied by a submatrix, 3 times 3 submatrix of P, which we will call A, equals calibration matrix times rotation matrix. We can also write the calibration matrix as upper triangle matrix with K33 equals 1. We will express the rotation matrix as a vector of row vectors. This allows to write as the multiplication of calibration and rotation matrix as scaled row vectors of the rotation matrix. We are actually interested in second and third row. At first, you can see that the third row is just scaled third row of the rotation matrix. And the second row can be written as k to 2 times second row of rotation matrix plus k to 3 times third row of the rotation matrix. We will use it later. First we will write what is the third row of rotation matrix. Let's start by writing A as row vectors. If we normalize the third row of A matrix, we will get third row of R matrix. It is 0, 0, 1 vector. Let's look now what is F times the second row of A matrix. It is a multiple of third row plus some multiple of second row of the rotation matrix. So we can see that it is in a plane, it is a vector in the plane which bases are R2 transpose and R3 transpose vectors. We also know that the rotation matrix has each vector perpendicular to each other and they have unit norm. So we know R3 transposed and A2 transposed. And we can see that the vector which is perpendicular to these vectors is R1 up to scale. Therefore, we first compute the vector, let's call it R1 transpose prime, as a cross product of A2 transposed and R3 transposed, which is 12 minus 16 and 0. And next, R1 transpose will be R1 transpose prime divided by its norm. It is 3/5 minus 4/5 0 vector. If you look again to the picture, we can see that R2 is perpendicular to R1 and R3. If R1 and R3 are normalized, therefore it's just cross product of R3 transposed and R1 transposed. It is 4/5 and 3/5 0 vector. We can see that the rotation matrix we are looking for is rotation around z-axis about approximately 50 degrees. As the next thing we will estimate the calibration matrix and focal length. So let's start with the focal length. We see that the focal length times A matrix equals K times R matrix. So we can also see that the focal length times R3 transpose equals R3 transpose. This relationship holds also for norm of these vectors. Therefore, we can write the focal length as a norm of R3 transpose, which is 1, divided by norm of A3 transpose, which is 0.1. So the focal length is 10. The last unknown is upper triangle matrix K. As FA equals KR, we can write FAR transpose equals K. So if we assign the values, K will be the matrix 100, 0, 0, 0, 200, 0, 500, 400, 1. That's it, we have a calibration matrix, rotation matrix, camera center and focal length for our projection matrix B. The next third task is to find the camera projection center C in delta with following projection matrix. So we will apply the same approach. We will compute the null space of matrix B. In other words, we are looking for any multiple of first, second and third column to get the fourth column. So we can see that, for example, -1 times second column will give us 0 vector. Therefore, C delta is 0, -1, 0. In the fourth task, we should write down coordinates of all points in three-dimensional space that projects on a line V equals 0, where V is the second coordinate in the image. Therefore, the projection equation will be lambda times a vector u01 equals p times some three-dimensional vector x extended about 1. This equation gives us lambda u equals x1, 0 equals x1 plus x2, and lambda equals x3 plus 2. Therefore, x1 is lambda u, x2 is minus lambda u, and x3 is lambda minus 2, where u and lambda are some real numbers. In the last example, we have a vector u in beta, and we want to express the transformation of alpha to beta. This vector u in beta has coordinates 2, 3, and 0. The beta coordinate system has center in O, and the alpha coordinate system has center in C. Therefore, we would like to define alpha such a way that u has coordinates 2, 3, and 2. Therefore, alpha 3 is 0.5 beta 3. And the matrix of alpha vectors in beta is 1, 0, 0, 0, 1, 0, 0, 0, and 0.5.